All right, section 9.4. Today we're going to take a look at permutations and combinations. There is a symbol that you may or may not be familiar with that we'll start with. The symbol is an exclamation point. It's actually called a factorial. When you see in factorial, it means we take n and we multiply it by the number less than n and the number less than that one, all the way down to multiplying it by 3 times 2 times 1. So wherever we start, we just go all the way down to 1, multiply them all together. That's factorial. By definition, and you'll see why we need this to be our definition, but the definition of 0 factorial, because it's obviously less than 1 already, right? So this first definition doesn't work, is that 0 factorial equals 1. Yes?
So I understand with the n minus 1, n minus 2, but then why is there like a 3 times 2 times 1?
Because you all go all the way down to 1. You just decrease the number multiplying all the way down to 1. Wherever you start, you keep multiplying all the way down to 1. Okay. Let me show you the first example, and maybe it'll make sense. It's 4 factorial. So we take 4, and we multiply out all the way down to 1. 3, 2, 1. So we include all the numbers from that number down to 1, and we multiply them.
So n would be 3 then, right?
In here is 4.
Oh, 4, right.
Yeah. Yeah.
4 and then minus 1. Okay.
Yes. Now, 4 times 3 times 2 times 1, what does that equal? Somebody said it, 24. Yeah. Now, these can get big pretty quick, as you can see, right? It was 4 factorial, and it's 24. And if you did 5 factorial, it'd be 120. Because we multiply this by 5. And if you multiply it by 6, the numbers get bigger very, very quickly. So there are values that we're going to see used where our calculator cannot support. For example, we'll be doing some stuff with cards at some point in this lesson. Your cards, right, there's 52 cards in a deck. If you used the number 52 and you put in 52 factorial in your calculator, and there are some factorial buttons if you want to know where they are on your particular calculator, we'll look. But your calculator cannot support 52 factorial. It will turn it into scientific notation because it's too big. That's not helpful. So we don't want it turning it into a scientific notation. We want it keeping it in standard form. So typically when we're working with factorials, we reduce a lot of things before we ever actually do multiplying. Okay? So a couple other things. This section is titled Permutations and Combinations, and that's fine. But it's really more about like ways of things happening. Right? How many ways can something happen? So this particular theorem is back in chapter 2. If you have had number theory, you saw it there. If not, it's not a problem. But it talks about what happens when you take 2 events and you do them sequentially. So if event M can occur in little m ways and event N can occur in little n ways, then if you follow event M followed by event N, it can occur in m times n ways. When I teach this in number theory, we talk about putting together an outfit. You have so many shirts, so many pairs of pants, so many pairs of shoes. How many different outfits do you have if they're distinguishably different? Right? It's almost like the picture that they would do like in the Chili's kids meals. I don't know if you've ever seen it when they say, look at the 2 pictures, find 7 differences between the 2 different pictures, right? You're looking for all the things that are different ways of doing something. We're doing this with our events. So the example I have for us today is Pizza Planet, which is from Toy Story. Pizza Planet offers 3 kinds of salad, 15 kinds of pizza, and 4 desserts. How many different meals consisting of 1 salad, 1 pizza, and 1 dessert can you make? How many of them? So we would take each of those events, right? We have an event of choosing a salad, and it says there's 3 salads. We have the event of choosing a kind of pizza. There's 15 kinds of pizza. And we have the event of choosing a dessert, and there's 4 different kinds of desserts. And the fundamental principle of counting says if we multiply these together, that's the total number of different meals that could be created. So if you have a calculator, grab it. What is 3 times 15 times 4?
180.
180 is right. So there's 180 meals. And the fundamental principle of counting pops up in our work that we're going to do today. That's why I mention it as well as the new ones that we're going to be establishing in this section. So let's go into permutations now. There are a couple of types of permutations. The one you see on the front sheet says permutations of like objects. If you flip a couple more in, you're going to see we're going to talk about permutations of unlike objects. So let's talk about what we mean by like objects. Like objects are things where you can't tell them apart. So imagine having a bag of Skittles, or my example here is a thing of Starburst, right? I can't tell one pink Skittle away from another pink Skittle. They're both pink Skittles, or red, or whatever color you want. They're indistinguishable. If you were to look at the plate of meal, the plate over here, well, that's not a good example. Another place where we see these used are when we're trying to figure out, that's not a good example either. So what happens when you try to come up with something on the spot? Okay, if I think of another one, I'll mention it. All right, the way that this works is we have a total number of objects, that's our N. Okay, so we have a total number of Skittles in the bag or Starburst in the container or whatever. And then the R's are the distinguishable differences, right? So there's, in like a standard package of Skittles, we've got purple, red, green, orange, and yellow. I think there's 5. So we'd have 5 distinguishably different colors of M&Ms where we can't, or M&Ms, Starburst, where we can tell them apart. There's 5, all right? And then what goes underneath is how many of each of those 5, in this case, there are. So it's the number of pink Skittles, it's the number of purple Skittles or blue Skittles or red Skittles or whatever colors of things we're looking at, all multiplied together with factorials. Okay? So the number on top is the total number of Skittles. All these R's on bottom add together to be the N. Okay? Because they're how many reds we have, how many purples we have, how many greens we have, how many yellows, and how many oranges. And then we do factorials for each one of them to take away the distinguishably different pieces. Okay, so let me show you how it works. It's actually pretty straightforward. We have in our example a package of Starburst. In our package of Starburst, there are 4 red, 5 pink, which is the best color, 3 yellow, and 2 oranges. So the first thing we probably need to establish is how many Starbursts are there? 14. So we would add them together. 4 plus 5 plus 3 plus 2. We have 14 total. Is that good for everybody? That's the number that goes on top. You see, if I wanted to know how many different ways could I eat the Starburst, well, I would multiply 14 times 13 times 12 all the way down to 1. But some of those don't make any difference. It doesn't matter if I eat red Starburst 1 first or red Starburst 2 first. They're both red Starbursts. They're not distinguishably different. So it's almost like you're removing those pieces by dividing by them. So we divide by each of the different pieces that aren't able to be distinguished. Namely, the 4 that are red, factorial. The 5 that are pink, factorial. The 3 that are yellow, factorial. And the 2 that are orange, factorial. 14 factorial might be small enough your calculator can tolerate it, but this is a good opportunity for me to show you what happens if it's not. Okay? Did it work?
I said, does it cancel out?
Yes, everything cancels out. These will always end up in whole numbers, which should make sense because I'm supposed to be finding a number of ways of something happening. There can't be a decimal number of ways of something happening, right? So like conceptually, that should make sense. So what we do is we write down the 14 factorial times 13, so 14 times 13, 12, 11, 10, 9. Now, you can write it all the way down to 1 if you want to. I'm going to stop at 5, and I'll show you why. The denominator has a bunch of factorials in it, and the biggest factorial in the denominator is 5 factorial, right? So the 5 factorial that's in the denominator, it's about right here when we write the other ones out, is going to completely cancel with the 5 factorial in the numerator Because if I wrote them both out, they'd say 5 times 4 times 3 times 2 times 1. So I'm just saving myself a little bit of writing. But the other ones don't have that luxury. We need to write them out. So there's my 4 times 3 times 2 times 1. I have a 3 times 2 times 1. And I have a 2 times 1. And the first thing that happens is I cancel out the 5 factorials. Okay, is that all right so far? If you want, you can multiply everything on the top, multiply everything on the bottom, and divide. That's fine. But like Braden pointed out, or asked the question of, are they going to cancel out? The answer is yes. So we can actually force them to cancel out if we wish as well. For example, the 3 times 2 is the same as the 6, so those can cancel. Let's see, I have 4 times 2 here. That's 8. That will cancel with the 8. I can't cancel exactly like wholly cancel the 3 and the 2 that are left. There's a 3 right here, and there's a 2 right here. But I can reduce them with things, right? For example, the 3 and the 12 are both divisible by 3. So I can just divide them both by 3. So if I divide 12 by 3, I have 4. And if I divide 3 by 3, there's that 1. Right, I'm dividing. The 2, same thing. I can cancel it with whichever one you wish. I'll do it with a 10. The 2 divides 10 and leaves me with 5. Now, some of you have very neat handwriting, and this is not going to be a problem. Others of you do not have as neat handwriting, and you have to be really careful because it's really easy to lose numbers as you're starting to cancel pieces out because the pieces don't always cancel out in order. So be real careful as you're doing this that you don't lose anything. So let's see. We have 14, 13, 4, 11, 5, 9, and 7. Random assortment of things, right? 14 times 13 times 4 times 11 times 5 times 9 times 7. Now, do you have to write them all out? No, but you're going to need to put them into your calculator at this point. Mm-hmm. So you're going to multiply all those values together with the help of your calculator because nobody wants to do that by hand. And what are you going to get?
I got 2 million. Does that sound right?
Mm-hmm.
2,522,520.
Mm-hmm. Out of one little bitty package of Starburst. Crazy, right? Okay, I remember another example. I think this one shows up in your book. It talks about running flags up a flagpole, like colored flags. And so you've got a stack of reds, a stack of blues, and a stack of purples or whatever, and you're running the flags up the flagpole. So it doesn't matter, if you put purple flag 1 and then purple flag 2, or purple flag 2 and then purple flag 1, it's the same thing. That's another one that shows up in your homework, I think, or your group work about indistinguishably different or like objects. Yes, Asia.
I may not just be getting this, but how do we know the difference between, let's just use, for problems like example 2 and for example 3, like how are you supposed to know which one to use, like the fundamental principles of counting or the permutation?
Yeah, so the fundamental principle of counting involves different events happening.
Okay.
We had an event of choosing the pizza, an event of choosing the salad, and an event of choosing our dessert. This, we're eating all the Skittles or the Starburst, or we're running all the flags up the pole. There's just one event.
Okay.
Yeah. And we'll have that same question pop up probably as we go because we'll have some more questions of when does this get used. All right, anything else on that one? Okay, our last two types of problems are things where we have unlike objects. So a really good example of unlike objects is people. That's our easiest example to think of when we're thinking of unlike objects as people. So we have a whole bunch of people doing something, and it would not be the same if I had Asia doing it as if I had Elizabeth doing it, right? It's whatever thing we're doing. It's different depending on what's going on with the people involved because they're distinguishably different. So the two different things we have left are what are called permutations and combinations. And big old bold, I've got it in red on my screen. The key thing that makes these two things different is whether the order matters. So the order matters in a permutation. And over here, in a combination, the order does not matter. Okay? So we're going to just do the two problems, or like talk about the two processes and do a problem. And the problems themselves show an example of cases that are similar, but when one of them the order matters and in the other one it does not. So there's a notation here. There's a little n at the beginning. You've got a capital P for permutation, and then you've got a little r after it. We read this, when I read this, I read this as n choose r. So what I really have is I have n objects, right? So in this classroom today, we have 3, 6, 9, 10, 11, 12, 12 of us if we count me. We'd have 12 objects for the purpose of discussion. R would say, I need to choose 3 of you to do a task. Okay, so it's how many you're choosing from what you're choosing. If we were working on our Starburst example over here, and we were thinking about the candies, I wouldn't be eating all of them. The permutation here of like objects has me eating the whole thing of Starburst. Right? I'm not choosing just a few, I'm choosing the whole bag. So over here, when I'm talking about permutations, I'm talking about choosing just a few from among my choices. You'll need to notice the definition of what NPR is it's n factorial on top, the total number, just like it was for the last problem, n factorial on top. And the denominator n minus r factorial is exactly how many I'm not choosing, right? So if I had 12 people and I was choosing 3, the denominator 12 minus 3 is the 9 people I don't choose. Okay, so the denominator actually ends up being the number they're not being chosen, because it doesn't matter what order they can be rearranged in, they're not being chosen to begin with. That's why they're dividing out. So here's an example of such a thing. 30 contestants put their names in a hat for a raffle. First place wins $100, second place wins $50, and third place wins $25. In how many different ways can prizes be awarded? So there's a very good reason why it tells us amounts of money here. The reason is because the amounts that they win are different. So it matters whether or not you were chosen first or third, because your prize is different. Does that make sense? Those are distinguishably different prizes. So in this situation, it's not the people that are distinguishably different, although they of course are. It's the prizes that are different, which is why this is a permutation problem. Now, I do have 30 people I'm choosing from, and I do have 3 people that get to have those 3 prizes that are different. So the numerator is 30 factorial, right? It's all the different number of the ways I could have picked the people. The denominator is 30 minus 3 factorial. Or if you wish, you could jump all the way to this point where you say it's 27 factorial, your pick. It's the people who don't get prizes. I'm eliminating them from the multiplication process is what I'm really doing. So I'm going to write out 30 factorial, 30 times 29 times 28 times 27 factorial, and I'm going to stop because it matches the 27 factorial on bottom. Can cancel the 27 factorials, and I'm only left with multiplying 30 times 29 times 28, which is what?
24,360.
24,360 ways that those prizes could be awarded. Different arrangements of people, different prizes to different people. That's what's going on. Okay, so let's talk about how that's different from combinations in terms of the formula first. So this was my formula, n factorial over n minus r factorial. Abby?
So like when you stop at the 27, but
Yes.
what if the bottom number was like 3? Would you expect us to write
Yeah, so
all the way down to 3?
you would have to, I will tell you the calculator's not going to support that, which means their problems are not going to have you do that.
Got it.
The number ends up getting to be too large for your calculator to compute it exactly, and we're going to have exact answers as we work through these. Yeah. Okay, so combination-wise, the formula, just looking at the formula, obviously the notation is still n choose r. I already mentioned that order doesn't matter, which we'll talk about in a second, but I just want you to look at the formula. The formula is still almost the same. I have n factorial and I have n minus r factorial in the denominator. But the difference now is that I have an r factorial in the denominator as well. Okay, so that's the difference in the formula. Let me show you the difference in the problem setup with the example that follows. 30 contestants put their name in a hat for a raffle. That's the same. 3 people win $75. All the prizes are the same. They are not distinguishable, right? The prizes themselves are not distinguishable. And the reason that that matters is because that means that we have order doesn't matter. If I got pulled first out of the hat and I got pulled third out of the hat, I still get the $75. Make sense? Whereas before, if I was pulled first out of the hat, I got 100, third out of the hat, I got 25. Those are different outcomes. But my outcome is the same as long as my name gets drawn in this one that we're working with now. Okay? So as we're taking a look at how to process that, we still have that same 30 factorial. We still have the same 27 factorial. But what happens is we remove the 3 factorial as well, because it doesn't matter who gets first drawn, second drawn, or third drawn. That's 3 people we've drawn, and their order doesn't matter. It's almost like what happened when we were doing this permutations over here, where all the different colors, order doesn't matter, because for reds, doesn't matter if I draw red 1 or red 2, eat red 1 or red 2, it's the same thing, it's indistinguishable. So the awards here, the order doesn't matter who's picked first, so it's a combination. Just like on the last one, my 30 times 29 times 28 times 27 stops at 27. So the 27 factorial gets canceled. Notice you can only cancel stuff with factorials if they're exactly the same. Right, so you can't look at this and say, oh look, 30 divides by 3. Now I've got 10 factorial on top. No, you don't. So no canceling inside of factorials unless they're perfect matches. On the bottom now I have 3 times 2 times 1. So again, if you wanted to, especially since we already did the problem over here, the 24,360 and just divide by 6, you could do that. If you want to reduce it, you can do that too. 3 and 2 is 6. 30 divided by 6 is 5. So you could do 5 times 29 times 28. Either way, you end up with what? 4,060 ways. Okay, so if you were working with these kinds of ideas with, elementary, middle school, it'd be middle school, let's be real. It'd be middle school age. They would not have them all shoved into the same section. You guys understand that, right? They'd have one of these things and they'd do like 20 problems that all had the same kind of a flavor to them over and over again to get the hang of it. You're going to be thrown into doing all of them, and we'll do this next time, where you don't know which one to use and you don't know which one to use right away. Right? Your children in your classroom wouldn't be doing that. They'd do 15 problems of permutations of like objects, and then they do 15 problems of permutations with unlike objects. And then eventually at the end, they might have and probably would have some section where they're randomized and they have to pick. You're starting out with randomized and have to pick when we come back next time. Yes? Do you have a question, Asia?
No.
Okay. All right, so I'm going to stop here. The other half of this video I will post from my other semesters of teaching it somewhere along the way. If it doesn't quite correspond, I'll tell you where to start your video watching so that it starts in the right place. You'll watch that video on Friday or thereabouts, and then we'll come back on Monday with homework completed and group work from this section, both.